This podcast is a summary of what we call the mass laws, which are a series of observations and laws in history that led to the discovery of the atom. So observations that led to an atomic view of matter. The first one is probably the most famous, which is law of conservation of matter. And it says that matter cannot be created or destroyed. So if you have a reaction, before the reaction, we can weigh everything. After the reaction, if we weigh everything again, it has to weigh exactly the same amount. If it creates a gas in the reaction, if a gas is formed, remember that gases have mass, and so they will add to the mass of the final reaction. The law of definite composition says that when you have a pure compound, it always has the same ratio of elements. So for example, if you form water in a reaction, it is always going to be 2 parts hydrogen and 1 part oxygen, and that's going to make water. That ratio of 2 to 1 is never ever going to change if we have formed water. However, there are some atoms that can combine in different ratios to make different compounds. Nitrogen is a really good example of that, and I've shown some pictures. Nitrogen and oxygen can combine in a ratio of 1 to 1, 1 to 2, 2 to 1, and 2 to 2. And these are all totally different compounds that have very different properties. We also can see that CO2, which you might be familiar with, carbon dioxide. Carbon and oxygen can also form CO, which is carbon monoxide. Carbon dioxide is a gas, and it's safe. It's a byproduct of photosynthesis or respiration, and carbon monoxide is a deadly poisonous gas. Totally different properties, even though they're both made of carbon and oxygen, but the ratios are different. So describe each diagram in terms of elements or compounds. They're labeled with bromine and fluorine, orange and yellow, and which one best exhibits the law of multiple proportions. So go through A, B, and C, shut off your video, go through A, B, and C, label them elements, compounds, if it's a mixture, and then figure out which one shows the law of multiple proportions best. When you're ready, turn the video back on. Okay, so in terms of elements and compounds, this one has 2 elements, C also has 2 elements, and B is the one that best exhibits the law of multiple proportions because the yellow and the orange are combining in 2 different ways. 1 orange to 3 yellows, and that would be BRF3. And it's also combined in a ratio of 1 to 1, 1 orange and 1 yellow, and that would be BRF. Yep, and labeling elements and compounds. A is a mixture of 2 elements. C is a mixture of 2 elements plus a compound. So both of these would be mixtures. So how does the following diagram demonstrate the law of conservation of mass? Again, shut off your video, think about this for a second, write down your notes, and then turn it back on and check and see how you did. So we can see here, if we count up all the atoms, it has the same number of purple atoms on the left and on the right. It has the same number of green atoms on the left and on the right. And I didn't add them all up, but they are exactly the same. And so all they have done is rearrange. We have not lost or gained any atoms. So that's how this diagram demonstrates the law of conservation of mass. Exactly the same number of particles, just rearranged to make something new. So we are going to look at the mass ratio, mass fraction and mass percent of the three elements in calcium carbonate, which is CaCO3. So first, we're going to list the three elements, the name and the symbol. And they are calcium, which is Ca, and notice that the second letter in an element symbol always has to be lowercase. So capital C and lowercase a is calcium. C is carbon, and O is oxygen. The mass fraction is the mass of an element divided by the total mass. So that's going to give us a decimal number. And then the mass percent is you take the mass fraction that you calculated up here and you multiply it by 100 to change it to a percentage. It's really the same information. So we're going to fill out this chart for calcium carbonate. The total sample is 20 grams, and in that 20 grams, the mass of calcium is 8 grams, carbon is 2.4, oxygen is 9.6, and notice they have to add up to 20, which makes sense because all of that 20 grams has to be accounted for. So go through in this chart, calculate the mass fraction, calculate the mass percent, and we'll see how this all fits together. So the mass fraction, again, is for each element, the grams of the element divided by the total, which is 20 in each case, gives us a decimal. So the mass fraction converted to a percentage, 0.40 means 40% mass percent. And again, look at the totals. The total is going to be 20 grams. The total mass fraction is always going to be 1, and the total mass percent always has to be 100%. So here are some math problems, and I would definitely use a ratio form here. Go through, use the chart on your page to figure out questions about calcium carbonate with different amounts. So here we have a sample that's 16.5 grams. How much carbon would it have? Use a ratio in the chart above, and stop your tape, go through and try to figure these out, and then turn it back on and check and see how you did. So setting it up as a ratio, mass of carbon over the total mass of carbon, which is what we're looking for, which is X, divided by 16.5, which is our new total. Solving for X, we get 1.98 grams of carbon. So here we're looking for 35 grams of calcium, and we have to figure out how many total grams of calcium carbonate we would need. So again, 8 grams of calcium over 20, that ratio is always exactly the same. That's what the law of multiple proportion says, or the definite proportion says. We're looking for 35 grams of calcium. How much total would we need to get that? Again, cross multiply, solving for X, and we get 87.5 grams. So for these diagrams, go through and determine, is it pure or a mixture? If it's a mixture, what type of mixture is it? Does it contain elements or compounds or both? And is it a solid, a liquid, or a gas? Shut off your video and go through and try to label these. It takes a while to do these, and then turn it back on and check your answers. A couple things to note. Notice that the gas is shown by particles that are far apart from each other, and they're also moving. We show these by little whooshies. The liquids are close together, bumping up next to each other, but they don't hold their form. They're sort of sloppy and moving around. Again, liquids close together, but they take the shape of the container and they don't have their own form. The solid, however, does show its own form, and none of these are showing a solid.